Alright, 12-3, all about infinite series and infinite sequences. First thing we're going to look at here is how to find the limit of the terms in an infinite sequence, and then after that we'll take a look at how to find the sums of an infinite series. So when you work with sequences, like an infinite sequence such as this one where the pattern's pretty predictable, with 1, 1/2, 1/3, 1/4, 1/5, realize that the general term is 1 over n, as you can see right here. We can take a look at each one of these sequences, sequence terms, and look at it as if we were to graph it. It looks something like this. So when we look at these terms here, as we go from 1 to 1/2 to 1/3, these terms start getting smaller and smaller and smaller. And what's happening with these smaller and smaller and smaller terms is that they're approaching a value. And if we were to continue to do this forever, the 100th term, the millionth term, the billionth term, we'd end up approaching a fraction that's pretty close to being 0. And so what we call that concept is a limit. 0 would be called the limit of the sequence. And we can express that limit just like this. And then we could read this here as the limit of 1 over n as n approaches infinity equals 0. So let's look at how we can calculate limits. So if we look at this particular sequence here, 7, 7/4, 7/16, so on and so forth, we can figure out what the limit of this is if we look at substituting large values for n if we can write the general form for the sequence. So let's do that first. Let's write the general rule for the expression. Now the trick for writing the general rule for the expression is understanding that this particular sequence is a geometric sequence, which require us to use the general rule. You know, we just did this in 12-2, ace of 1 times r raised to the n minus 1 power. So now when we write this rule for ace of n, a couple tricks we have to know here. First of all, we need to know that what the first term is. The first term is 7, so that's easy. To find r, if we take the second term and divide it by the first term, 7/4 divided by 7, we end up at 1/4. You can also notice this if you just go from term to term. The 7 kind of stays put, and we're just multiplying by 1/4 each time. So there we have our general rule, 7 times 1/4 raised to the n minus 1 power. And so if we were to continue to look at this pattern, increase n and increase n and increase n, we can get a good feel for what's happening here. And as we keep on increasing n and taking that quarter and raising it to that power, this 1/4 becomes less and less and even less until it's practically non-existent, because that fraction is pretty close to 0. And so what impact does that have on the 7? Well, it makes that 7 become less important. And by important, I mean it makes it become closer and closer to 0 too, because that 7 is getting multiplied by that number that's close to 0. And so we can express this as the limit as n approaches infinity of 7 times 1/4 raised to the n minus 1 power. And we can say that limit is equal to 0. Wait a minute. Did you guys hear something? Wait, there it was again. Oh boy, now it's obnoxiously loud. Hey, I know what that is. We're looking for a... Yeah, cool trick. So, one cool trick you can do here is when you find that general rule, you can type that function into your calculator. 7 times 1/4 raised to the x minus 1. And then start looking at those x values as they get larger and larger and larger and larger. And what you're going to notice is that when we increase those values, it starts to approach that limit of ours, which was 0. So let's try this cool trick on some of these problems here. And I know I could probably go through this here, going through the same calculator tricks here, but maybe we can kind of shortcut this and show you those even cooler tricks. I don't have a fanfare for that, but even cooler tricks to show us how we can get these limits to happen quickly. So looking at this particular limit here as n approaches infinity, one thing to notice is as n gets really, 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 really large, a couple of terms in these sequences in the numerator and the denominator start to become irrelevant. And those are the lesser powers. And really as you get larger and larger numbers for n, the bigger the power, the more it overrides the other powers. So what tends to happen here in this case is with this particular problem, the positive n squared kind of takes over the numerator as we go towards infinity. And down below, the 2n cubed starts to take over here. And so in this situation, realize that when you pit these two n's together, numerator and denominator, really the denominator is really what's going to take over here and make this fraction get smaller and smaller and smaller and smaller. So in these situations here, the limit here as n approaches infinity is going to be exactly 0. Notice in this example the bigger power is taking over here, and notice where those are at. Right there with 5n squared and on top, and then with n squared down the bottom. Now in these situations here where no numerator or denominator really have the upper hand here, what we need to do to find this limit quickly is we can take the leading coefficient and divide it by the leading coefficient. And so now we arrive at our limit here of 5. So now with this example here, once again, notice the biggest power in the numerator and denominator are here. Notice in this case, the numerator wins this one. So when we have a bigger power on top than we do on the bottom, that means you're always going to have a number that's going to be bigger than 1. And as n gets increasingly larger, you're going to have an increasing number greater than 1. It's going to keep on getting bigger. So in these situations here, we have no limit. So to sum this up, when the degree of the numerator is less than the degree of the denominator, the limit will always be 0. When the degree of the numerator is equal to the degree of the denominator, the limit's going to be the leading coefficient divided by the leading coefficient. And when the degree of the numerator is greater than the degree of the denominator, then there will be no limit. Now, let's take care of the other objective, which is finding the sum of an infinite series. Now, if we look at this series here of 1/5 plus 1/25 plus 1/125th, and we continue in this pattern here, we can find a sum for this. And to wrap our heads around the sum in class, what we talked about is, let's just use this sum as if it were a finite sum. So then we would need to use the finite sum formula. So if we were to do that, we'd have something that looks like this, and we'd have to come up with a number here. So what would this look like if we were trying to find maybe the sum of the first 10 terms? Well, it'd look like this. We put our first term in there of 1/5, put the first term in there again of 1/5. Notice that when we do the 1/25th divided by the 1/5, we get our constant ratio here of 1/5. Lots of fifths here. We raise that to the 10th power, and we divide by 1 minus 1 over 5. Now, to get our heads wrapped around an infinite series, what we did in class here is we said, well, what if we made this not 10, but maybe, say, 100? What happens when that becomes 100 is now that whole quantity that you see there kind of grayed out becomes less here. It becomes closer to 0. And as we keep on increasing the number of terms we're adding up, the more insignificant that of a value that we have right there working in the numerator there. So now it just seems like we're really just taking our 1/5 and doing it by 1 minus 1/5, just like that. And so that's where our formula comes from. We can modify the finite sum formula to look something like that. And so there we go. Now, the only way this formula works, the only way it works is when we have an R value that is less than 1. Notice that our R value here back in this problem was 1/5, less than 1. When that common ratio is less than 1, what's happening with each successive term is they're getting smaller and smaller and smaller and smaller, which means we can kind of cut this off at a certain point, because at some point we're going to be adding something that's pretty much almost exactly 0, which means that we can have a sum on this thing. Let's do it with to an example. So let's use this formula and let's figure out how to find the sum of an infinite series. Because the R value needs to be less than 1 for even this sum to work, that's something that we should approach first when it comes to any problem. And if we can find R first, we can determine whether or not we can even have a sum for a particular problem. So let's look at this one on the left, and let's find R. Notice here I'm taking the second term and dividing by the one before it to give us 1/3. So now with this 1/3 here, we quickly notice that since that r value there of 1/3 is less than 1, there will be a sum. So let's go get it. So now substituting those numbers in there, we put the first term in there of 3/4. We divide it by 1 minus 1/3, progressing here at simplifying it. We're going to take 3/4, divide it by 2/3, or we can just multiply by the reciprocal to arrive at our answer here of 9/8, or 1.125. Let's look at the other example. This one here, once again, let's find r. So we'll take the 3, we'll divide it by the square root of 3. No need to get fancy here. Let's just divide it. Throw it into the calculator and just look at our r value. We get about 1.73. So no sum can exist here because we have an r value that's greater than 1. Okay? So that's pretty much all there is to it with 12.3. Be able to find the sum of an infinite series and be able to find limits to sequences using, for the most part, these 3 tricks that you see here, these generalized forms.